All right, good morning, everybody. And today we're going to cover chapters 5 and 6. Again, I'll have everything posted up hopefully by this evening. I've been stumbling on a couple of these videos. But this first one, chapter 5 deals with inverse functions, exponentials, and logarithmic functions. And we're going to look at all those. To begin with, you have to remember a couple of things. First, we have to review chapter 2, section 3. Oops. That was the composite function one. So if I had f of x equals x plus 2, g of x equals 3x minus 5, then I could take a composite function so whenever you see this, this is read f of g, the function f of the function g of x. So what that means function f, its function variable is g, whose function variable is x. So it looks like this. It just kind of collapses over itself. So the way you solve this, or you simplify it, first off, whatever's on the right-hand side or inside the parenthesis, put that in first. Just the equation, because we don't know what x is. It's just a variable. So we know that g of x is this entire equation here. So I put that in place of g of x. I put this in the equation. Now what that means is whatever's in my function f, whatever's inside the parentheses, whatever x is, I put 3x plus 5. So f of x is x plus 2. This goes in place of x. So this is my g of x. It's taking place of x. Now I just simplify. Negative 5 plus 2 is negative 3. So that is my composite function f of g of x. Again, composite functions, you put one function inside another and you compound them. We're going to be using this concept in a very short while to prove that an inverse exists. Okay, let me see. Okay. Okay, well, fx is a function. If it is 1 to 1, then it is continuous and an inverse does exist. Now, what is 1 to 1? I'm using this symbol from now on, 1 to 1. One to one means this. For every value x, there is one and only one value of y. It's not g, it's a y. Remember that one? Where? It's O-N-E, yeah. O-N-E. Remember, in chapter 2, we looked at number sets. How can we tell that that's one-to-one? Each x is different. That's the first. If each x is different, it's automatically one-to-one. If two or more points have the same x value, they must have the same y values. That's one-to-one. All right. In chapter 2, we look at it this way. Yeah. So each x is different. So it doesn't matter with y, it's automatically this one's one-to-one. We also look at it this way. A, B, C, D, 2. This is one-to-one. Each value x, each of these, the domain values, go to one and only one y value. A, B, C, D. Is that function one-to-one? Because all the x's are different. It doesn't matter if it's only one y. If they think of a classroom, each of the students are individuals, and they all have the same teacher. So this is one-to-one. Now, if a function is one-to-one, then it has, has an inverse. If a function is one-to-one, then it has an inverse. Graphically, what does that mean? Let's look at the cubic function. Does this one have an inverse? Is it one-to-one? How can you tell? Yeah, yes. We're looking at it. How about this one? Yes on this one, no on this one. Not one-to-one. Yes, it is one-to-one. Graphically, if I give you the graphs, the horizontal line test. Remember, earlier in chapter 2, we used the vertical line test. Well, that's to see if it's a function. If it is a function. If we could draw a vertical line up and down anywhere and hits the graph only once, then it's a function. Now, it's one-to-one if we draw a horizontal line and it crosses the graph only once. Then it's one-to-one. So horizontal line test. The horizontal one, it tests for one-to-oneness, uniqueness. The vertical line test sees if it's a function. To prove a function is one-to-one, this has to be true. So you have a function, whatever the function is. If I pick two values, A and B, the only way these two answers can be equal only if A equals B. So let's say we had the equation 2x plus 5. Is this function one-to-one? Well, let's see. First off, let's take f of a. So anywhere C and x, we put an a. So we have 2a plus 5. On this side, it's 2b plus 5. Solve for the letters. We subtract 5 from both sides. We have 2a equals 2b. We get to a by itself, so we divide by 2 both sides. That's how you prove one-to-oneness. Let's try that again. Let's try with x squared. Is this function one-to-one? So again, in order to test it mathematically, we have to test, are the y values, the only way they could be true is if a equals b. In other words, if a equals b, then it's the same number inside there. So we have a squared equals b squared. So this is f of a equals f of b. get rid of the square. We have to square root both sides. Whenever you square something that's square root something that's squared, you get a plus or minus that answer. So is this 1-to-1? No, because let's look at positive A. It can equal positive or negative B. Negative A can equal positive or negative B. So this is not 1-to-1 because for any A, it has to equal B for sure, but we can't tell which one's which. Notation. What's the symbol for inverse? A function looks like this, f of x. An inverse function, -1 exponent. Whenever you see that -1 is an exponent, you know it's an inverse. How to find an inverse? 2 steps. Step 1, change x and y. Solve for y. That y is now written as inverse of y. All right, so let's look at an example. Example, f of x equals 2x minus 3. Find the inverse. Really quick, let's go back to these 2 examples here. What kind of line graph is that? Linear. So its graph, it crosses through 5 up 2/2, so it looks like this. Does it pass the horizontal line test? Yeah, so that one is 1-to-1. This one looks like what? It's a parabola, x squared. It fails the horizontal line test, so it cannot be 1-to-1. All right, so I forgot to put the graphics to it. So that's what we're looking at. That's what we mean. All right. So remember, we only have 3 steps. 1, switch x and y. So f of x is the same thing as y. So we switch x and y. Then second is solve for y. Add 3 to both sides. X plus 3 equals 2y. Then we have to get the y by itself, so we divide by 2. So y is equal to x plus 3 over 2. That is my inverse function. Remember, y was 2x minus 3. We started off with this, we found the inverse. How do you test an inverse to see if it's really an inverse? If y inverse is an inverse, then these two things have to be true. Y of y inverse has to equal x. And then likewise, the inverse of y of x also has to equal x. All right, so we had our original equation 2x minus 3. We think we found its inverse. We have to perform two tests. F of F inverse. But that says it's or we collapse it to go this way. So what is this? What is y inverse? That's this equation here. Now, this x plus 3 over 2 is inside of parentheses, so it belongs to the x values of the y. And y is 2x plus 3, so it's 2x minus 3. Basically, all it's telling me to do, whatever's on the inside, that equation goes inside the outer function. That's all it does. So now let's simplify. 2 and 2 cancel, leaving us with x plus 3 minus 3. Plus 3 minus 3 cancel, we end up with x. That's only the first way. That's y to y inverse. Let's do the other way. The second way, y inverse of y. Remember our functions. So what this one says is our first question, that's inside there, goes in place of x in the second. So anywhere I see an x, I put a 2x minus 3. 2x minus 3 plus 3 over 2. So I just took the first equation, put it in my second. That's what it says. Take your first equation, put it inside the second. Let's work it out. There's no coefficient, so we don't need the parentheses. On top, we have to work on them separately. You have -3 plus 3 leaves me with 2x over 2. The 2's cancel, leaving me with x. So that's how you prove the inverse exists. You do the composite function of it. The last thing in this section, restricting the domain to make a function one-to-one. Okay, here's our equation, y equals x squared. It fails the one-to-one test because of the horizontal line, right? So that's because we took the domain as all real numbers. If we changed our domain to only read from 0 to infinity, in other words, erase this side, is it now one-to-one? Yeah, because it passes. So we can restrict the domain to make it one-to-one. So that's perfectly legit. All right, section 2. Exponential functions. Until now, x has always been the base. I'll come back to this word in a second. Now, x can be an exponent. So, in the past, originally, we had y equals x to the third, or something, x any exponent. Remember, this is our exponent, or power. And this number down here is called the base. Now we can have an equation that looks like this. The exponent is our x, and the base is a. It's a number. But there are conditions there are conditions here. A cannot equal 1, and A has to be positive. It cannot equal 1. So very important, because now we're going to get this. So an exponential equation looks like this. F of x equals a to the power x. Let's look at the graphs. For a greater than 1, the graph looks like this. Remember, anything to the power 0 is 1. So its y-intercept is always 1. Whenever x. If your exponent is 0, I don't care what the number is, it's always going to be 1. This is the graph. It has a horizontal asymptote at 0 at the x-axis. So that's if x is greater than 1. Remember, all the other one says it has to be greater than 0. So the other aspect could be, what if a is between 0 and 1? So in other words, if a is a decimal, a positive decimal, or a fraction, again. So let's look at this function. 1 over a to the power x. It's a fraction. Anything to the power 0 is 1. So there's 1 again. It's always going to cross through 1. But now what happens is the graph has been switched about the y-axis. It rotates. So this is an example of y equals 2 to the power x. This is an example of y equals 1/2 to the power x. So far, so good?
The 2 or 2x?
There's a 2x. This is 1/2. Oh, I'm sorry. Yes. Good catch. Good catch. That would have been a boring graph. So if the base is a solid number bigger than 1, it looks like this. It's an increasing function. If it's a fraction between 0 and 1, it's a decreasing function. Let's look at the properties of exponents. The properties of exponential equations. Y equals ax. So the first thing, they have to be continuous. There's no stopping points, no breaking points. They're 1-to-1, meaning they'll pass the horizontal line test. The domain is all real numbers. The range, remember, you cannot get a negative answer with exponents, exponential equations. So there's no x-intercept. It's an increasing function. Increasing function if a is bigger than 1. It's a decreasing function if a is between 0 and 1. The horizontal asymptote is always the x-axis. Well, again, if there's transformations, it'll move, but it's the x-axis. The horizontal asymptote equals 0. So y equals 0. And the last one, the y-intercept is always at 1. Y equals 1. You're going to need, whenever we do exponential equations, you're going to need calculators because the numbers get really, really weird. Well, yeah, but the other part is logarithms. You'll need it for there too. So use calculators. That's okay. Okay, so we know that 2 to the power x all we know is the graph looks like this and crosses at 1. Let's look at some transformations. What do you think that means? X minus 2. What kind of transformation is that? Because it affects the x, it's a horizontal transformation. It's a horizontal shift. 2 to the right. Remember, the graph originally looked like this, but since I shifted the origin to here, the graph shifts to here, and it still crosses at 2, 1. This one here was 0, 1. It's now at 2, 1 because I moved the whole graph 2 spaces to the right. Well, yeah, because remember in horizontal shifts, set that equal to 0 and see what x equals. So it's positive 2. So we shifted to the right 2 spaces. It's always the opposite of what's inside there. Yes, it does. But these are the last, what we covered today, the last 2 of our library functions. The only two we haven't covered are the exponentials and logarithms. Okay, what if I gave you, let me see what's over here, 2x minus 4. Let's look at that equation. So remember, the original equation is 2x. So it looks like that. All it said, there is no horizontal shift, no x plus minus. All there is a vertical shift. Go down 4 spaces. So the x-axis drops down 4 spaces. 1, 2, 3, 4. There's the new x-axis. Remember, it's always the origin that shifts. The new origin's down here. The graph remains the same. The graph remains the same. It's always one step above the x-axis. So if here's the new x-axis, there's my y-intercept, and there's my new graph. And lastly, let's look at this one. Looking at this equation, is there a horizontal shift? No horizontal shift, it's just x. But the base of x is a decimal. That means that it still crosses at 1, but it's a decreasing function. But it's a negative in front of that. So I flip across the y-axis. My graph now looks like this. So this is 0.5x. This is negative 0.5x. What does this 5 make us do? Yeah. Yeah, so we take the horizontal axis and we move it up 5 spaces. 1, 2, 3, 4, 5. So there's a new x-axis. In our last graph, our intercept was 1 below the x-axis. Same thing here. Here's the x, so there's a y-intercept. Again, to get accurate numbers, you got to use a calculator. I'm just sketching these, but I think the computer wants at least 2 or 3 points so you can figure out where to go. So far, so good? I already covered the properties, didn't I?
Those were the properties of the exponential function.
Okay, I covered those. Yeah. So there you go. Let's look at some. Okay, yes, those are examples. So here's an application problem. Using exponentials. Remember, whenever you hear exponentials, that means x is the variable on top of the power. This is an example of future or compound interest. What compound interest looks at is P is the principal. That's the money borrowed. R is the percent rate at which you borrow it. N is the number of times a year you compound the interest. So it's the number of times. Annually means 1. Semi-annually means you do it 2 times a year. Quarterly, you do it 4 times a year. Monthly, you do it 12 times a year. And daily, you do it 365 times. So again, it's all of these words that break down to numbers that's put in there. And T is the amount of time in years. So let's say you borrowed $10,000 at 5% interest. Oops, sorry. $10,000, 5% interest. You have to convert it to a decimal, which is 0.05. It has to be a decimal. You do it monthly, and you're going to keep it for 3 years. So far, so good. So what this does is our equation, the P, the principal, is 10,000. 1 plus the rate is R, so it's 0.05 divided by N. What is N? 12, very good. To the power N times T. Twelve times 3. That'd be 36. So yeah, you punch that in your calculator, make sure you put parentheses and everything there, and they'll give you an annuity. This will give you the total amount of interest due on the $10,000 borrowed. A mathematician named Euler decided, well, what if I borrowed $1 at a rate of 100% for 1 year? In other words, P is 1, so there's nothing in front. 1 plus 1 over n times n. What he noticed was this. As x goes to infinity, goes further to the right, a approached a number. Where's that? 2.718 1 2 7 2718 2718 28 18 284 2.718 28 18 284, and it goes on forever. I'm not repeating. It's so that number is what we call E. And that's what we call Euler's constant. Because it in business and engineering, E is very, 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 very important because it is a set constant looking at how something compounds over infinity. So if we look at the graphs of these guys, again, this is an exponential equation. So the graph of this one crosses through 1 and it goes up. But again, the actual individual points are different because it's times 2.718. But the graph, the shape looks the same. This one shifted to the right, how many spaces? So 1, 2, 3. So there's my new origin, and it crosses at 1. This one, it's a fraction, so it's a decreasing function. It's negative, so it's below the x-axis. It flips across the x-axis. And this one, e to the power 2x looks like this. It crosses through 1 again. But since it's negative, we flip it across the x-axis. So because it's negative, we flip it across the x-axis. And that's E, because we'll be using those in the next couple of sections. Logarithms. Up until now, every one of our functions has always had an inverse. This is a function we deal with. This is from the library of functions, and here's its inverse. So, for example, x squared. Its inverse is the square root of x. X cubed its inverse is the cube root of x. An exponential equation, its inverse is the logarithmic equation. This is red. The log base A, there's the base, of x. Basically, what this says is this. Log base 2 of 8. What it says here is this. The logarithm means this. What power do you need to raise 2 to get 8? That's what it means. That's what the whole logarithmic function is about. The answer is 3, because 2 to the power of 3 is 8. And this is going to be very important in a second. The pattern is which is written. Okay. Convert between exponentials and logarithmic equations. Log base A of x is equal to y. The way you convert this thing is take the base. But remember, this is called the base. It's always going to remain the base. As I said up here earlier, then what power do you have to raise to the base to get 8? Well, yeah, in that case, yes. But in this one, so what power of A gives you x? So what happens here is this base comes here and pushes up that y. So we have A to the power of y. If the base is gone, the log drops off. So all we're left here is x. So that's the conversion. So log base 3 of x equals 2. So convert it, take the base, push up the answer. So it's 3 squared equals x. 3 squared is 9. To answer your question, what have to 9 should go here? So 3 to the power 2 equals 9. How about if I gave you this? What does that equal? It is, we don't know what that is. So we take the base, push it up. So it's 10 to the power x is equal to 10,000. Well, 10,000 is the same thing as 10 to the power of 4, which we have 4 zeros. Since the bases are the same, x equals 4. How about this one? Log base 9 of 3. This will take some thinking. Okay, you set it up like this already? Okay, so since we have different numbers here, we want them in the same base. Because this is 3 to the power 1, this is 9 to the power x. What is 9 made up of? 3 times 3. So this is 3 squared to the power x. So we have power to a power, so we multiply 2 times x is 2x. Since the bases are the same now I can compare the answers. If the bases are the same, that means the answers have to be equal. So 2x equals 1. Divided by 2, x equals 1/2. Yes. Yeah, I'm sorry. My big old fat head. There. Yes. Now, what does that mean? X is 1/2. 9 to the power 1/2 simply means the square root of 9, which becomes 3. What do you think so far? A lot of, yeah, but that's just it. I mean, once you have the step by step, I know that's a lot of stuff to remember, but it's all, if you have a formula sheet, which I'll send to everybody, then you have it all. Let me see. Oh, properties of logs. First property. Log A MN. Whenever you have a log of a multiplication, a product of something, you can split them up by adding the two numbers. And it's still the same base, log A. So log of base 5 of 3x would equal log base 5 of 3 plus log base 5 of x. Because this is a product, I can split them up. This is called the product rule. Okay, if you have more letters, like what if you had 3xy? Then you'd have 3 equations. Whatever's multiplied together, you just put a plus sign in front of it. The second one, the quotient rule. What does quotient mean? Right, fraction. Log base 5 of m over n. Since when you multiply things earlier, it makes things bigger. When you divide, it makes things smaller. So here we subtract the top minus the bottom. So our example would be log base 5 of x over 4. That would be log base 5 of x minus the log base 5 of 4. The power rule. Log base a, any base, it could be any base. Log base a of x to the power n. You cannot have exponents when you deal with logs. So that exponent comes out in front. For example, log base 5 of x to the third. The exponent goes out in front. So it's 3 log base 5 of x. Okay, 4. The identity. Log base a of a. If the base and the number are the same, it equals 1. Log base a of 1 equals 0. Again, we could look at these using the transformation. Remember, take the base. So it has a to the power 1 equals a. So if you have the same base as the number, it equals 1. And the same thing here. A pushes up to 0. Anything to the 0 power is 1. Let's do a couple of. So here's the thing you would remember. If you're multiplying, you always have plus signs in front of the logs. If you're dividing, whatever's on the bottom will have a minus sign in front of it.
So
Z. Yes. Said. So expand this one. Because this one, you can't really do much with it, so you have to expand it. Remember, anything on top has a plus in front of it, anything on the bottom has a minus. Yeah, and if we had m down here, it'd be a minus log m because it's on the bottom. So there you go. That's expanding. Oh, we're not done yet because we have exponents. We can't have exponents. They have to go in front. And there's your answer. Okay, what if I give you this? Shrink it, consolidate it. So remember, this thing has a plus. Anything that has a minus in front of it goes where? On the bottom. Very good. And any coefficient goes where? It becomes a power. So this is log base a of x to the fifth, log base a of y, log base a of 2 to the 1/4 power. Since they're all log base a's, since all of them are log base a's, I can now consolidate them. This one's plus, this one's a plus, and this one's a minus. So that means I have a fraction. The pluses go on top, and the negatives go on the bottom. The only thing we can do is this exponent. X to the fifth. Since it's a fraction exponent, it means it's the 4th root of 2. If you have a fraction exponent, whatever's on the bottom goes inside the root. And there's your answer. Yeah, you have to be able to go both directions. If I give you a condensed one, expand it. If I give you expand it, constrict it. Oh, here's. You'll have some of these in homework. If log of 2 equals 0.03 and log, well, I'm going to say, for simplicity purposes, I'm going to say log of 2 is 4 and log of 3 is 5. It tells you what they are. So what if I gave you this? Log of 6. We only know what log of 2 and log of 3 are. So what is 6 made up of? 2 times 3. So since they're multiplied, log of 2 plus log of 3. Since they're multiplied, I can split them up. And log of 2 was 4. Log of 3 was 5. The answer is 9. Makes sense? That's another one. Is log of 3 over 2. Yeah, we're pretty close to being done. It's a fraction, so it's subtraction. The top minus the bottom. Log of 3, we said is 5. Log of 2 is 4. 5 minus 4 is 1. It's just a matter of substituting him in there. We have to break the equation down to make it doable. What about if I gave you this one? What would you do?
Just by itself.
Log of 5. Now we knew that log of 2 was 4. Log of 3 was 5.
Could it be like the reverse?
What do you mean?
Like 5?
Oh, no.
Okay.
No, that's good. I never thought about that, but good thought though. That's a pretty good thought. This one has no solution. Because you cannot go 2 plus 3. There is no rule that says you can add. We have a rule that says if we multiply, then we can add. But there's no rule that says anything like that. So that one has no answer.
I really thought it was gonna be like reverse.
I was pretty good thinking, but no. Oh. Change of base. Your calculator, for the most part, doesn't have this. Doesn't have a base 2 button. What you'll see on your calculator is usually these two. It's ln, yeah. This is called a natural log. This is called a common log. So since you have a base 2 here, we can't do anything with it. So the change of base formula does this. Here's the change of base formula. Log base A of m over n. No, let's just say m. Log base A of m, no fraction. We can convert it using common log by taking the log of the numerator of the number divided by the log of the base. So whatever's here goes on top, whatever the base is goes on the bottom. You see, now they have a common log. Now they have a common log. You can use a natural log also. It would be ln of the numerator divided by ln of the base. Yeah, so let's go back. Let's not make it a fraction just yet. It's going to make it too cumbersome. So what would you type to get the answer in your calculator? Because whatever's here goes there, whatever is there on top.
Did it give you the same answer if you use like both?
ln, or yes, good question. Because it's the proportion that you're looking at. It's the ratio of numbers, so it's going to be the same answer. Very good question. Yeah, so log of 3 over log of 2 will give you the same ratio as ln 2 because it's the ratio you're looking at. I just introduced log and ln. We've been using log based on numbers. There are 3 types of logs. Depending on their base. Base 10. Our numeric system is base 10. If you count from 0 to 9, 10 fingers. 10 to 19, 21. So we have a decimal system, 10. That's what decimal means. Because it's what we use, we call this the common log because it's what we always use. So log base 10 of x is written log of x. If there's nothing down here, it's automatically base 10. Base E, Euler's number. We call that the natural log. So log base E of x can be written as ln of x. So if you ever see ln, that means for natural log. And you know it's automatically it's log base E. The log with nothing is base 10. Anything else is log base A of x. These are very important because you'll need those whenever you solve things. Log base 8 of 8 equals 1. Because whenever the base and the number are the same, equals 1. What do you think that equals? Well, that is one of the theorems, yeah. Well, two of the theorems. If you have an exponent, what happens to that exponent? It goes in the front. So we have m log base 8 of 8. And we have another theorem. What is log base 8 of 8? Yeah, we just did it here. So it's m. So whenever you have a base, and if the bases are the same, then it's just the exponent. How about if I gave you this? Oh, this is my dad's big. Good. Good. Yes. Ooh, yes. Yes, good point. Let me give you a call. I might work right now. Let me give you a call. Right. So what does ln stand for? Which is what? Log base E. You can't have an exponent, so that goes in front. If the base and this number are the same, that equals 1. The rule is this. If they're the same number, then it equals 1. How about this? The answer is m. Because this 4 is a base of that exponent, and this 4 is a base of this logarithm. If the bases are the same, they cancel out. You just have whatever's there. It also works with E. Remember, ln is log base E. So the bases are the same. They cancel, so it's just 5. So you have to be that's why you have to know those 3 conditions, the formulas. If you see ln, you know it's log base E. If the bases are the same, they cancel, just that. Log base 4, the 4. Solving log and exponential equations. We have 2 properties. We have 2 properties for solving these equations. First one is the base exponent property. It's this. If you have 2 exponential equations, same bases, then the answer is simply the exponents, because the bases cancel each other out. Property of logarithmic equalities. If you have 2 terms, same log, same base. If the log base A, the only way they can be equal is if m equals n. So that's what we're looking for. We're trying to get using one of these 2 properties to solve these equations. Okay, since obviously 3 and 20 don't have anything in common, so we're trying to get the x out of there. The easiest way to do that is you can raise them to whatever power you want. So I'm going to raise both of these equations by log base 3. Because if these 2 are equal, that means their logs have to be equal. Log base 3 of 3, the x goes out in front, so it's just x. And since our calculators don't have log base 3, we have to use a change of base. Log of 20 over log of 3. That number goes on top. This number goes on the bottom. That's how you'd solve it.
There's specific reason why it goes through.
Well, yeah, I chose it to get rid of that one. If I could choose 20, then I have a 1 over here. And I have some other stuff. So whatever the base of your exponent is, raises that power. You use that log. Makes it much easier. Look at that. You full of good questions today. Let's see another example. Oh. So you see here, I mean, neither one of them are good. Because if you do ln4 or log 4, this will get, but you still have this one. So it's easier here. Let's take the ln of both sides, but it's easier to write. That means the exponents come down. Remember, we're solving for x. So we have to get rid of the parentheses here, so we distribute. So it's x times ln4 plus 3 times ln4. Since all the x's on one side, non-x's the other, we're going to add ln3 here and subtract 3 ln4. We want this one over there and that one over there. So plus x ln3, that's this one, equals minus 3 ln4. All right, now we're solving for x. They both have an x in common, so I can factor it out. We have two of them that are added together. What can they become? Four times 3 is 12. Last step. Divide by ln12. So we have x equals negative 3 ln4 over ln12. lot of writing, but it's the same principles. We have to get, since the x's are the exponents, we have to get rid of them. So I put ln on both sides. They come out in front. Distribute to get rid of the parentheses, move all the x's to one side, and solve for x. Same story we've done forever, but new stuff. This is going to take us back a while. Remember when we first did exponents? What does a negative exponent really do? It puts it on the bottom and change the sign. Because if we have x to the power -2, that's the same thing as 1 over x squared. It's all a negative exponent does, so it makes it this. Okay, since we have fractions and an equal sign, LCD. The only denominator we have is e to the power x. Multiply it to each term. On both sides. Reduce. That's the only thing that reduces the EX on the bottom. That's cancellation. So multiply. E to the x times e to the x is e to the 2x, because you same basis, you add the exponents. So it's e x plus x is 2x plus 1 minus 6 to ex equals 0. Okay, let's put these in order. So we have e2x minus 6ex plus 1 equals 0. We have 3 terms, and the first one's 2x. If we take the middle term, multiply it by 2, we get the first term. So this is quadratic in form. So we solve for the middle term. A is 1, B is -6, C is 1. All right, so you just plug them in there. I'm not gonna do that here. So you just plug those values in there. Let's say we had e to the x equals plus or minus 4. That's our final answer. So we have e to the power of x equals 4, e to the power of x equals negative 4. You can't have a negative answer because the range is positive 0 up. How do you solve e to the x equals 4? Since e is log base e, so take the ln of both sides. Ln e cancel. I know it's easy when I do it. But again, do what you can. And next week, we still have all next week to go over all these if we need to. All right. So that does it for chapter 5. Chapter 6 is short and sweet. Systems of linear equations. We can solve by graphing. Substitution method. Elimination method. And Cramer's rule. So let's look at this. What is a system? 2 or more equations with 2 or more variables. That is a system. All right, so I'm going to use this example for all the methods. We have line 1, line 2, okay, first method we're going to use is the graphing method. We have 2 equations. We need to graph them. So we have to, when we graph them, you have to put the equations in y equals mx plus b format. That's what we did in chapter 2. So here, I can subtract the x from both sides. Negative y equals negative x plus 5. Change the sign across the board because you can't have a negative y. And there's our first line. And the second one, solve for y. So we have to subtract 2x from both sides. So now we have them that way. Let's go ahead and graph them. So let's graph the first one. Graph the y-intercept was at -5. The slope is 1. So it's 1/1, up 1/1. Connect the dots. Do the same thing with the other one. Plot the y-intercept. It's at +1. The slope is -2/1, so it's down 2/1. And connect the dots. Where they intersect is the answer. So it looks pretty close to 2, -3. That'd be my guess. Again, I could be wrong because my graph sucks. So that's graphing. Take both the equations, set them equal to y, and graph them. The next method is substitution. We have our 2 lines again. Substitution does this. Choose either line. You want is line 1 and line 2. Let's choose line 1. That equals x minus y equals 5. That's the first of the steps. Second step, solve for a variable. It doesn't matter which one, just solve for a variable. Since x is positive already, I'm just going to add y to both sides. X equals y plus 5. We'll come back to that one later. Now, plug that equation into the other line you didn't use. So we have x minus y equals 5. This is line 1. I added y. X equals y plus 5. Since I used line 1 there, I didn't use line 2. Anywhere I see an x, I put a y plus 5. I substitute y plus 5 in place of x. So x equals y plus 5. So anywhere I see an x, I put a y plus 5. Work it out. Work it out. So distribute, get rid of the parentheses. So 2y plus 10 plus y equals 1. Solve for the variable. Combine like terms. 2y plus y is 3y. Get rid of the 10. 1 minus 10 is negative 9. Divide by 3. Negative 9 divided by 3 is negative 3. So that's the y value. So we have the y value. What do we need now? The x value. Well, the x value is right here. Plug that solution into the equation in step 2. Because we have y, we just need x. We know x equals y plus 5. So y is negative 3 plus 5. X equals 2. So our solution is the point 2, negative 3. That's what I guessed. Because normally my graphs are so horrible, I'm off by a ton. So this is, if you look at, we get the same answer we did last time, where the intersect was 2, negative 3. So that's substitution. Pick an equation, solve for a variable, plug it into the other equation, solve for that. That's one part of it. And then plug that into what you got the first time. That's substitution. Now let's look at elimination. The steps for elimination is first, decide which variable to eliminate. They have to have the same number, only different signs. So you may need to alter it, change it by multiplying one number across the whole thing. So looking at this equation, the easiest variable for me to get rid of would be y, because here's y. They both have the same coefficient, different signs. Add the two lines together. So x plus 2x is 3x. Negative 1y positive, they cancel. 5 plus 1 is 6. Just add the two lines together. And solve for the variable. So divide both sides by 3. X equals 2. Now, plug that solution into either of the original lines and solve for the remaining variable. So see what we did here. We had two equations. Since we see that the in front of the y has the same number of different signs, we just add the two equations. We did that. Solve for x. Now we can take this x equals 2 and go to either one of these two equations. The easier one, I always pick the easier one. So the first one. So I chose line 1. I plug anywhere I see an x, I put a 2. And solve for y. Subtract 2 first. Change the signs. So y is equal to 3. And your solution is x, y. So it's 2, negative 3. And all three of them the same answer.
It was positive 3, right?
Yes, because it was negative y equals positive 3. I have to have a positive y, so I change the signs. Now, those are the first three methods. The last method, the last thing we're going to talk about in this class is Cramer's rule. Uses matrices and determinants. And I'll explain those in a second. So whenever you hear 3 by 3 matrix, that means it's the number of rows by the number of columns. So the first number is the number of rows. Second number is always the columns. And a matrix is written inside these brackets. Each row constitutes an equation. Each column represents the variable. The only thing that goes inside the matrix are numbers. There are no letters inside there. Well, some we'll have it. So if I had the equation 2x plus 3y minus 5z equals 2, negative 1x minus 2y plus 4z equals 0, 6x minus z equals negative 3. So this first one's line 1. What goes inside here are the coefficients of x, y, and z. The coefficient of x is 2, 3, negative 5. Equals, yeah. Yes, they can. But remember, if your initial equation has fractions in it, or if it has decimals, convert them into fractions. And if it has fractions, remember what we did earlier? Find the LCD, get rid of the fractions. So you can do a little bit of front work to make it easier for you in the long run. So line 2 are the coefficients of the second equation. Negative 1, negative 2, 4. And in the answers, it's 0. These are the solutions. This part. So 6, there is no y, so it's 0. Negative 1, negative 3. So that's how you convert equations to matrices, and you can also work backwards. In other words, if I gave you this matrix, what would be the equation that came from the system? Well, these are first one's the x's, this is the y, this is line 1, this is line 2. Very good. Very good. Yeah, so you work both ways. Now, the determinant we're only going to be dealing with 2 by 2 matrices. So we have A1, B1, A2, B2. We only have those. The determinant is simply multiply that diagonal. So you have A1 times B2 minus the other diagonal, A2 times B1. That'll give you some number. So let's look at our we just did. 2, 4, negative 3, 1. Remember, this is the original matrix. So it's this diagonal, which is 2 times 1, minus the other diagonal, 4 times negative 3. Negative 4 times negative 3 is positive 12, so it equals 14. And you would, since that's the main determinant of the equation, we call it D. So D is 14. All right, let's look at our example. Let's do this, and I'll show you how to find x and y also. So here we have our 2 equations. X minus y equals 5. 2x plus y equals 1. Convert it to matrices first. So in this first line, the coefficient of x is 1. The coefficient of y is -1. The answer is 5. 2, 1, 1. So from here on out, we're only going to be using these two matrices. Oh, that's +1. I'm sorry. It's +1. So the first thing we have to do is find D, the main determinant. The main determinant is the determinant of the original equation, the left side. So this multiplied 1 times 1 minus the other direction, 2 times -1. 1 plus 2 is 3. So the D value, the determinant, is 3. Did you convert it wrong?
So I was gonna ask, like what's the pattern to that? Like, explain it?
Yeah, the pattern of it is the main diagonal first, from top left to bottom right. That's the first part. Then always minus the second one. Yeah, the sheet I'm going to send you, it's all color coded. But now we have to know what the x and y are. So the d sub x. Remember our original matrix. This is the x column, this is the y column, these are the solutions. Since I'm solving for d sub x, I take the answer column and put it in place of x. Because now it's a solution and the y. Because I'm looking for the x, I need to have that part. Again, it's this multiplication, 5 times 1 minus that direction. Negative and negative is a positive, 1, so it equals 6. So my d sub x is 6.
Would be the other way around for the one.
Yes. So I put the solution in place of y, leave the x alone. So that's x in my solutions. Because yeah, whatever the subscript is, that's the column you replace it with the answers. Leave the other one alone. One times 1 minus 2 times 5. So my d sub y is -9. So far, so good. Now comes, we have to know what x, y, and z are, or x and y are. So to solve for x, I take dx over d. Because if I look at it this way, the d's cancel, I'll just left with x. So dx was 6, d was 3, that equals 2. Y is dy over d. -9 over 3 is -3. So my answer is that. Cramer's rule looks like it, but it's the easiest of all the methods. So all it is addition, multiplication, and addition. So any one of those four methods you could use on the final. That's it.
The final's gonna be like all of them, right? All time.
1 through 6. Yeah, if I can't get rid of the 7 and 8 part, I'll just give you all the answers and let you all just put the answers in and not get dinged for it. All right, so that does it for the course. That means your next thing is next week when we come back for Thanksgiving. We'll go over whatever homework assignments you want and get ready to do a practice test or two for the final. It's all up to you guys. Any questions? No questions?